Okay, this is going to be a short video to continue with our study of logic. I believe in our last lesson we looked at the three main forms of conditionals. If you didn't jot those down, I've got them on the screen right here. You might want to note these. You could take the back side of your note sheet that we had worked examples on the front side and jot these down. Just a quick reminder that this last case is different. The conclusion, that's what I'm using the Q for to represent the conclusion, is at the beginning, and the hypothesis, which we've got with our P, is at the end. So that one does switch. And if you need a short little key, make yourself a key that says P is your hypothesis and Q is your conclusion. Today we're going to actually look at a different form of a logic statement that I haven't introduced to you yet, and you probably have not heard of, but I'm going to work with an example and then we'll get to that. So here's the example. Congruent segments are segments with equal measures. And I know I'm kind of giving away the punchline here because I went ahead and showed you the conditional and the converse. So let's go ahead and identify our hypothesis and conclusion. And it really is hard to tell with the statements as far as which is the hypothesis and which is the conclusion. So don't worry too much about that when it's not in any conditional form. If it's already in one of your conditionals, you have to identify it correctly. But since this beginning statement wasn't even a conditional, I'm making it into one. I just kind of stick with general. The hypothesis is at the beginning. So there's my hypothesis. Segments are congruent, the P. And then my conclusion is at the end here. They have congruent measures. So I'm going to ask myself, is this a true statement or not? And remember that we determine truth value by making the hypothesis true. We have to satisfy this. Does the conclusion follow? So I can't pick segments that aren't congruent because that wouldn't satisfy the hypothesis. So I have to pick segments that are congruent. Sometimes a visual is helpful. So I don't know, I'm going to draw a little picture here. And I'm going to say that if I have segment AB and then I have segment CD, and if I have tick marks on them, and I know AB is congruent to CD, does it follow then that AB is equal to CD? So remember this notation that I kind of introduced to you in chapter 1. And I said don't worry about it too much, but they do mean different things because right here we're talking about the segments are congruent, the physical things are congruent. And here I'm talking about they have equal measures. The lengths of them are the same. But what ends up happening here is hopefully you're realizing that it's impossible that they don't have equal measures if they're physically the same thing. It's always going to be true. So the truth value for this one is going to be that it is always true. I'm going to put a little note here that it's true. And I know I haven't really proven that. We're going to right now focus on proving things false by giving a counterexample. And basically I can't come up with a counterexample for this conditional statement. So I'm going to say that it's true. Now let's look at the converse. So converse, I've now got segments have equal measures is at the beginning here. So that's my hypothesis. And then my conclusion is they are congruent. So we switched the P and Q from above is what I'm showing you here. The Q is at the beginning and the P is at the end. Now let's take a look again and see if this is going to be true. And if I take a look at my example that I have up there, well, if I start with this time AB being equal to CD, they have the same lengths, then does it follow that AB is congruent to CD? Segment AB is congruent to segment CD. And in this case, well, once again, I have two things that have the exact same length. Aren't they going to be congruent to each other? And I'm getting a true again. And you're probably thinking, duh, it has to be true. This is super obvious. Well, what we have is we have a definition here. So we've agreed that for definitions in the form of logic, we're going to make a special type of statement that we use so that we don't have to go through this every time of write it both ways, determine it's true both ways, and it's super obvious. So what we're going to do is we're going to take our statement that we have. We're going to chop off the beginning of it right here. The if, we're going to take out the then. We're going to start with segments, so I'm going to capitalize that. Segments have equal measures. And then we're going to put this word in the middle. I guess it's a word. I double F. It's if with another F at the end. That's intentionally spelled wrong. If, because that if isn't really just if. That if stands for if and only if. So I have two options. I can either write if and only if, or I can put I double F and we read it as if and only if. And what it means is it means that I have a statement that is true both ways as a conditional and a converse. So we only use this if we have two cases of true. Then we write it as a shortcut, so we don't have to write the conditional and the converse and establish both of them as true. We call this a biconditional statement. So let's add this to the list that we have here. We have conditionals. Now I'm going to add what we call a biconditional statement. And it's going to be, although it really doesn't matter if you do P or Q at the beginning because it's true both ways. And then my connector word is going to be let's see if this shows up. That IFF, and if you want to make a note for yourself, that stands for if and only if. Oops. Ignore that line that I just drew. Here, will erase it. If and only if. Oops, sorry about that. So there's one other thing that I wanted to note here, and that would be that we also can use arrows. You might have noticed that I did that in the last problem. So if you want to use arrows, I'll just put that over here. For the conditional, we tend to use the arrow with our P and our Q. We use P implies Q is almost what I say. When I do the arrow, we use an arrow to the right, versus the biconditional, because it's true both ways. We do an arrow to the right, but also to the left, a double-sided arrow. And that's one other way of noting that we have a statement that is true both ways, and we're talking about forms of logic. Last thing I have for you is let's go in reverse, and I'm going to just say, write the definition of a straight angle as a biconditional. So instead of having the two conditional statements leading to it, I just want us to take the straight angle and go straight to the biconditional statement. So I'm going to start, remember, we're not going to start with the word if. That's the most common mistake I see is people start with the word if. I'm going to start right with the hypothesis. And I sometimes think about it as a conditional. So I'm thinking if an angle is a straight angle, then what makes a straight angle? Hopefully you're thinking it has a measure of 180 degrees. Take that if out, so I end up with this. An angle is a straight angle, or you could say an angle is straight if and only if and this time I'm writing it out, but you could put IFF, that's accepted as if and only if it has a measure of 180 degrees. So we're going to actually practice doing this. You're going to practice doing this, and you're going to write all of your definitions that we're going to need to use as we continue through this chapter and continue through the year as biconditional statements. And we're going to make a habit of this, that we always write definitions as biconditional statements, because it turns out definitions, in order to be a definition, it actually does have to be true both ways. So not all of our postulates are true both ways. Not all of our theorems, which we're going to get to, are true both ways, but our definitions will always be true both ways. I hope that helps with what a biconditional statement is. Feel free to ask me if you have any questions.